guess it's time for us to start. So in this class today, we're going to wrap up chapter number 24. So I'm going to look at some applications for calculating the electric potential for some of these systems right here. So we're going to be looking at a ring charge, this. So this is actually my back here. This was supposed to be a line charge. So the example for the line charge, I think you guys had that yesterday. The drill. This one here. I was supposed to say that this is line. So we'll look at these three examples. Now let me just remind you that so when you have a system of point charges, you calculate the potential using this equation right here. So again, remember that there is nothing about looking at the direction, so there is no unit vectors, right? You just you sum all the values of Qi divided by Ri. And this sum, for example, this sum will run from I equals to 1 to n, where n would be the number of charges that you have in the system. Now, when you have a continuous charge, we need to do integral, and we do integral using this equation right there. So let me show, so again, just to kind of refresh. So as an example, let's suppose that I have something that looks like this. And let's say that we have a negative charge here. Let's say this is negative Q. And I have a positive charge here. Let's suppose that my point P, so my point P is sitting right here, such that the distance from, let's say the distance from here to here is B. And the distance from here to here is A. And the distance from here to here is also A. So what I want to do is that I want to calculate the potential at point P. And I know that because this is a system of charges, this is why I need to use summation here. So this is Ke, the sum from I equals to 1. So when you sum in this example, you're going to sum from I equals to 1 to I equals to what? 3. To 3. Because we have, so in this case, n is equals to 3. Qi divided by Ri. So remember, no unit vectors. This is a scalar quantity. So I'm going to make a small table here. I'm going to say that let my Q1 be equals to plus Q. So this is my Q1 here. And this is my Q2. And this is my Q3. So if my Q1 is equals to plus Q, what do you think should be my R1? That's correct. So R1 is this distance from here to here. So this is the square root of A squared. And then I can say that my Q2 is equals to negative Q. And what is my R2? B. And my Q3, again, this is plus Q. And notice that in this case here, my R3 is also equals to my R1 A squared plus B squared. So once you have all of these, we can just go ahead and plug it into this equation and run the sum, right? So if you run that sum, it's just Q1 over R1 plus Q2 over R2 plus Q3 over R3. Now, convince yourself that if you do this calculation, you end up with this final result here. So this is 2Q. So let's write this as this is KE. Then I'll put something like that. And then I'll write this as 2Q divided by A squared B squared minus 2. Do you guys agree with that? Yeah. Because the contribution from Q1 and Q3 are the same, right? So you just end up getting twice that value. So if I gave you something like this in the exam and I said that, let's say Q1 is 1.0 microcoulombs, Q2 is negative 1.0 microcoulombs, and Q3 is plus 1.0 microcoulombs. And then, for example, we can say let A be equals to 1.0 centimeters and B be equals to 2.0 centimeters. Now, if I gave you those numbers, you can substitute into that equation to get the numerical value, right? And the numerical value, if you do this correctly, you're going to get something that is in joule per coulombs. Because we said that the potential is the joule per coulomb. So this is just one example on how to use this equation here. So again, we use this equation when you have discrete charges. And so let me go now back to my PowerPoint, and then we're going to look at some examples for the continuous charge. So let me share, let me stop share here. I want to share. Okay. So look at this example. I think we started talking about this in the previous class with example number 24.5. So here, I want to calculate the electric potential from a ring charge. And so I think the main point to remember here is that when you calculate this potential, so this is my point P is sitting right here. Now, when I calculate, so when I run this integral here, because I want to integrate over all the charge that I have on this ring, I'm going to see that my dq does not depend on x. So for example, x is a fixed point, so I can pull all of this outside of the integral, and then the integral of dq just gives me the total charge that I have on the system. So it means that the potential at that point is just given by this equation. Now, keep this equation in mind because this is the equation that we're going to use to calculate the potential from a disk. So to calculate a disk, you start with a ring. So once you know what the potential is, you can calculate the x component of the electric field just by taking the derivative, and if you do that, you get this value here. So this is the x component of the electric field. So again, remember that the potential at point P for the ring is just equals to KA divided by this square. So if you take the derivative of this,